This morning is Professor Carlo Rovelli from the University of Marseille, and I believe he will talk about quantum gravity because his title is Quantum Spacetime.
Yeah, I am going to talk about quantum gravity. Kip is a wise old man, so he started off by saying, I'm not going to talk about quantum gravity. I am unwise old man, so I will only talk about quantum gravity. In fact, what I want to do is to try to offer my own perspective for where I think we are with respect to in the field of quantum gravity, particularly the field of loop quantum gravity. Subtitle is a physical theory without space and time. I will explain why and what I mean by that. If I have time at the end, I would like also to say something about a particular research direction which I'm particularly excited recently. It's very recent, it's just a few papers, so take it only just as information of something going on. One of the reasons I want to mention this at the end is to insist on the fact that I believe that unless there is a connection to observations, we are still in the realm of tentative speculations that may be completely wrong. And on the other hand, to sort of let you know that there is a constant effort to connect the abstract theoretical story about quantum gravity to concrete observations. Now, we have few certainties in quantum gravity, very few. So even the few we all share, let me try to disrupt them to you. And I'll start by showing one of the slides that Alexander presented the day before yesterday, in which he mentioned the schism between loop quantum gravity and string on the other hand, and called the two sides the canonical and the covariant approach to quantum gravity, where sort of loops is the canonical part and string is the covariant part. My last book, this is also an advertisement sketch, of course. It's called Covariant Loop Quantum Gravity. So it's loops, but it's covariant. Now, this is not at all to say that Alexander's effort to trace the origin of the schism was misled. To the opposite, I think it was right on the point where the two possible paths toward constructing a quantum gravity theory separated or formed. However, the simple identification, of course, canonical and covariant are just names. You can turn them in different manners. But the simple identification of one direction as the canonical one and that covariant one should be sharpened in some sense. And I will try to explain that as clear as I can, and this will be a main part of what I'm going to say. The Dirac effort to find methods to think about a theory, a quantum theory, and a classical theory, strong enough to work for generativity, is still at the origin of what we call loop quantum gravity, and the dynamics is entirely in that framework. The other way in which what I'm saying connects to what we heard in this conference in the first couple of days is very much regards these themes of geometrization of gravity versus physicalization of geometry, which has reappeared in various talks. And I think that to a large extent the way the covariant kinematics of quantum gravity has been developed in the last 2 or 3 decades, it's connected to this theme and is connected to the idea that generativity, of course, generativity in short is a discovery that the metric and the gravitational field are the same thing, right? That's a zero-level presentation of generativity, which you can present in two manners. There's no gravitational field, it's just a metric which has curves, or there's no metric, it's just a gravitational field that has some, can be interpreted in some cases as metrical. Now, to some extent, these are just two equivalent ways of a way of looking at the same thing. When you go to the quantum theory, the second one is much more powerful. It's much more powerful precisely because in the moment in which you start looking at the quantum aspect of the gravitational field, you can still call it space, of course. I mean, in fact, we do call it space all the time, space-time. But the spatial and temporal aspects or the features that we usually attach to the notion of space and time are largely lost. So it's much more convenient to think at this as to think at the object that we talk about as a field, a quantum field, and relegate the space and time aspect later. So allow me to conclude this introduction, then in a moment I will just give you the theory. Let's present the theory. But just to conclude the introduction, allow me to boldly present a slide in which the title is The Ontology of Fundamental Physics. It's, of course, a super simplified way. But I mean, according to fundamental physics, what the world is made of. And this is a 300 years of history in one slide, of course. And I've started even before Newton, because there was some mention of Descartes before, so I think it's not inappropriate to just step a little bit back before what is usually presented at the beginning of modern physics. Descartes has this matter that has a property of extension. Extension is a property of matter, which moves in vortices. Vortices, by the way. Newton constructed physics by separating the extension from matter and to a large extent, inventing this notion of space. I mean, it can be traced back to the ancient atomism, which also have a notion of space, but to clearly separating a notion of space from the bodies that were moving inside. Today we will say particles. So that's the ontology of physics in Newtonian physics. But I think Einstein would agree with that. The main step toward modern physics is the Faraday-Maxwell revolution and the introduction of the notion of fields, right? There's this beautiful page in the book of Maxwell in which he says, is fields real or not real? And there's a long one-page discussion, and this marvelous, he says, I would not go into this discussion unless I thought that it's crucial for our understanding of the world. It's beautiful. And he concludes, the gravitational field is real. Now, of course, what he means there, it has independent degrees of freedom, but I think it's very Einsteinian to interpret the Faraday-Maxwell evolution as the discovery that the world is not made by bodies, space, and time, but is made by one other entity, which is the field, okay, which Einstein strongly regarded as an entity by itself, at least in some phases of his work. And of course, special relativity is a sort of a discovered that we better think of this as a single thing. And quantum mechanics and quantum field theory is a remarkable discovery that elementary particles can be seen, in fact have to be seen, as quantum excitation fields. So like photons are quantum excitation of electromagnetic fields, electrons and quarks are quantum excitations of the Dirac field. So students today study physics as quantum fields in space-time, and that's many courses that, if you're a student, you go to university, that's how you're told physics is about. General relativity is the discovery that space-time is just one of the fields, or if you want, that one of the fields is space-time. So the notion of field and the notion of space-time get mixed in these general relativistic fields of covariant fields, whereby covariant fields I mean a field that has not to be thought as a pre-existing space, metric manifold, even manifold, with properties here and there, but an entity by itself. Okay? The jellyfish of Einstein booklet. Right? We're immersed in this huge jellyfish, which is an entity, and the insistence of Einstein that if you take away the gravitational field, what remains is not a manifold, is nothing. Now, if you want to do quantum gravity, you have to bring together the result that particle and field are the same thing, this quantum fields, with the fact that space-time is one of the fields. So you end up with a world which is necessarily described by just one entity or one family of entities, which are quantum fields, which live on top of one another, so to say, and whose manifestations, whose properties include particles, space, time, matter, sky, you know, people, voice, smiling faces, and everything else. This is what loop quantum gravity wants to do, to give a mathematical description of these covariant quantum fields, out of which everything else comes out. So I put the slides in the wrong order, so let me skip. This is loop quantum gravity. Okay, this is the end of the introduction, and I just decided to present the theory entirely in a single slide, in the sense in which you can say electromagnetism, you can just put a slide with a Maxwell equation, or in which the sense in which you can say generativity is just, you know, the Einstein equations, or maybe no, geodesic equation, a couple of equations. I'm not going to give you a lecture on the details of this mathematics here. I'm going to illustrate roughly what is here, but take this as a picture with the content of which will be filled a little bit slowly. But I want to somehow dispel the idea that the theory is a complicated machinery full of stuff and constructed by pieces. I mean, it can be presented in a single slide with a single set of equations. So how is the theory built? It's a quantum theory, so there's a state space, like in all quantum theories, and there's a bunch of operators. The state space is a Hilbert space, is defined as a limit, like Fock space, which is a standard quantum field theory. And its characteristic is that these Hilbert spaces here depend on this gamma. Gamma is a graph, are built on a graph, and they're not exotic things for people who study theoretical physics. Essentially, this is a standard Hilbert space of lattice gauge theory, an SU2 lattice gauge theory, so that the discretization of Young-Mill theory on a slide. The operators are the standard operator of lattice gauge theory. I'll tell you what the physics behind that in the next slide. This, of course, will be essentially the gravitational field. I'll tell you how. And so these are the state of the operators, like in quantum field theory, you know, the elementary courses for quantum field theory, you define the Fock space and accretion and annihilation operators. And then, quantum field theory, you give the Feynman rules. And the Feynman rules define the transition amplitudes, and these are the definition of the transition amplitude. So this is the kinematics, this is the dynamics. And the transition amplitudes are defined, there's a C here is a 2 complex, are defined order by order in some expansion, sort of a la Feynman. The term of expansion are labeled by this C, which are 2 complexes. 2 complexes are a set of faces, edges, and vertices, and they're defined by a certain integral of SU2. Okay. The key object in the integral is the amplitude associated with these vertices here, which is again an integral of SL to C. So SU2 and SL to C, the rotation group and the Lorentz group, enters into the definition of the dynamics. These objects here are the Wigner matrices, the element of the representation theory of SU2, and the analogous things for the unitary representation of SL to C, for those of you who knows this mathematics or this. So there are some well-defined mathematical objects that you find in mathematical books, and so that's it. This is the theory. Now, what is to be noticed here, the essential thing, is that there's no space, there's no x, there's no t, there's no asymptotic, there's no asymptotic state, nothing at all. So the theory is defined in terms of some states and some transition between states. Period. This transition between states are not transition depending on a time. There's no t here. Everything which has to do with space, time, particles should come out of that. One of the reasons, of course, I mean, some of you were at the debate with Gross and company yesterday, of the difficulty of talking to one another is that a particle physicist who look at this is lost. Where is the energy momentum tensor? Where is the asymptotic state? Where is time? Where is space? Where is Minkowski space? There is not. Okay, so most of the standard language of quantum field theory is absent here. Some pieces are there, but most of it is absent. Now, how did we, before I try to tell you a little bit more how we are there, how did we got there? This is a short, that's not history of loop quantum gravity, but it's a short my own account of where the main ideas come from. I'm not going to through all this. I just want to say that, of course, there is a Dirac ideas about how to do generalized quantum mechanics and how to do covariant transition amplitude, which obviously inform all that. In a sense, the transition amplitude are a sort of version of this integral here, which first appear in Meissner, as far as I know, and Meissner quotes Wheeler as the source of the idea. Maybe I'm wrong, it appeared previously. This is the integral, of course, that then is the basis of the intuition of the Hawking Euclidean quantum gravity. Regge discretization of GR, truncation of GR, it's one of the sources of that, of course, Wheeler and DeWitt. And Penrose, those graphs are, the state on the graph are spin networks in the sense of Penrose, so much of Penrose mathematics came into that. These are the sort of the deep sources of the both ideas and the techniques, the mathematical techniques behind that. Classical loop quantum gravity developed in the 80s and the 90s, the work of Ashtekar, the discovery. It started out from solutions of the Wheeler-DeWitt equation. Somehow, loop quantum gravity was born by realizing that the Wheeler-DeWitt equation admits solutions where, in a sense, the complexity of the dynamics is reduced to vertices, and that's what happens in the theory. The spectral results on the geometry, which I'll talk in a moment, is late 90s, and again in the late 90s, the idea of going covariant, of writing transition amplitudes instead of just studying the Hamiltonian constraint started to develop. This was made much more concrete in recent years, and the key results, which I'll say in a moment about the classical limit and finiteness, are not long ago. This version of the theory I'm giving you is one of version of the theory, right? It's not the only one. Loop quantum gravity now is a vast field with maybe 50 groups that work in the world. Some groups, like in Warsaw or in Germany, work on the purely Hamiltonian formulation, just using the Hamiltonian. There are works trying to connect the different versions, so on and so forth. I'm not giving a total overview of quantum gravity. I'm just giving you a sense of what I think is one of the versions, and the version where some of the best results have been obtained. So, this is a theory. Let me now tell you what one does with this theory, the key 4 results. These are the key 4 results. First of all, the states, this state in the Hilbert space have an interpretation in the classical limit as geometries. So 3-dimensional geometry and 4-dimensional geometry, I'll say later about 4-dimensional geometry. 3-dimensional geometry does emerge simply as a classical limit of the states in that Hilbert space with those operators, but only as a classical limit. If you look at the short scale, on the Planck scale, those states have the property that the geometry they describe is discrete. And I'll explain exactly in which sense this geometry is discrete in the next slide. This is a kinematics. As far as the dynamics is considered, there is a number of theorems which connect these transition amplitudes to the Hamilton function of general relativity, which is exactly what Dirac wanted at the beginning. Have transition amplitudes which are an appropriate limit go to the Hamilton function of the theory, from which you get the classical limit. More precisely, they connected to the Hamilton function of Regge gravity, which is a discretization of gravity, which in turn is believed to converge to the one of general relativity in an appropriate limit. And finally, this is the result on which everything holds, in a sense, and is the reason of the theory from the very beginning. Is this transition amplitudes are finite, and this is a theorem, order by order. For every C, these numbers is just a complex number. There's no infinity hidden there. They are both ultraviolet and infrared finite. More precisely, they are always ultraviolet finite, which is the key result. They are also infrared finite if you do the version of the theory with the cosmological constant, with the positive cosmological constant. So let me now come down from this very abstract and try to give you a little bit more concreteness of what is the story here. So the states live on these graphs. The operators are attached to links of these graphs. So given a node here, the operators attached to the need of this graph. And the operators, by the way they're defined, by the properties and by the gauge invariance, which is in the definition, in the very definition of the Hilbert space, satisfy a certain number of algebraic properties, which say that you can interpret them as describing the geometry of a polyhedron on each node. This is the little theorem by Penrose that goes back to a little theorem by Minkowski. So in other words, these operators are node by node a description of the local geometry. Now this is not surprising. I mean, the way it's presenting is a bit surprising, but it's not surprising because in a sense it's how the theory was constructed. Why SU2 gauge theory? Because generativity can be rewritten as SU2 gauge theory, and on a time slice, the triad is the SU2 electric operator, or more precisely the inverse triad. So the actual interpretation of these operators is just look how it's born, is the normal to a phase of a cellular decomposition of the state with a length proportional to the area. So once you have this reading of the operators describing the geometry, you can write for each one of the tetrahedron. Let's take each polyhedron. Let's take a tetrahedron, for example. You can write the area of each one of these faces. It's easily written in terms of basic operator or the volume. But now this area and volume are operators on this Hilbert space. So as usual in quantum mechanics, you can study the spectral properties of these operators. You can do just the quantum mechanics of these operators. And you discover that first area and volume form a complete commuting set in the sense of Dirac, like L, N, and NL and M for the hydrogen atom, or L square or LZ for angular momentum. Which means that you can write a basis which diagonalizes this operator, and most importantly, that they have discrete spectra. This is the spectrum of the area. The spectrum of the volume is more complicated, can be computed, I mean, have complicated formulas. This is some value of the spectrum of the volume for different areas. The spectrum is discrete, which means that there is a minimum value. So the geometry here is such that however you cut space, each piece cannot never be smaller than something. Okay? This is angular momentum. You have an angular momentum of an atom is discrete. If you cut an atom in quarks, angular momentum of the quark still cannot never be smaller than something. There's a minimum value of the angular momentum. There's a minimum value of area and volume here. So this is the origin of ultraviolet finiteness, because the ultraviolet divergences in Feynman graphs come from loops which are very small, right? High energy means. So it comes from the hypothesis that space is continuum all the way down to infinity. If you take the gravitational field and study its quantum properties, space is not continuum all the way down to infinity. So the ultraviolet divergences are just cut by quantum mechanics itself. More interesting, this is a basis, and I think this is the most interesting part also from the conceptual point of view. So I can diagonalize area and volume and have a basis here, which is labeled by the graph itself, the quantum number of the area, which sits on the links, so the area of its sides, and the quantum number of the volume that sits on the node. This basis is called the spin network basis. And the geometry is quantized in two senses. First, in two senses. First of all, as I said, the eigenvalues are discrete, so quantized like the energy of the atom is discrete. But most importantly, let's view it this way. Let's take a tetrahedron here. It has it has four faces and in the volume. So it's 5 quantum numbers. But the classical geometry of the tetrahedron is 6 numbers, right? 1, 2, 3, 4, 5, 6. So you have one less quantum number than classical quantities. It's exactly like the angular momentum. Angular momentum is jx, jy, jz are 3 numbers, but when you go to the quantum theory, you can diagonalize j square and jz, period, 2. Which means that there's always some fuzziness. One of the jy, jz, I mean, one of the some component of the angular momentum is always fuzzy, which means that an electron is not really a spinning stone. It's like a spinning stone, but it's a quantum spinning stone because it's always a fuzzy spinning stone. It's angular momentum as a vector is always fuzzy. Here's the same. The geometry of each node here is like a polyhedron only in some classical limit. In the small, it's always fuzzy because you cannot compute the geometry exactly because there's always some non-commutativity between the different geometrical variables. So, according to this picture, the geometry of the Planck scale is quantized because it's discrete, but more importantly, it's quantized because it's fuzzy. It's not really like that at all, right? Can be thought as a set of atoms of space, as Juan Maldacena put it yesterday on the blackboard, whose geometry is fuzzy. I think the most interesting aspect of all that is that these states here, so now we have a nice mathematics for describing its states, the quantum properties, but these are not states in space, right? These are states of space. So this is a simple picture of that. This is standard quantum field theory. You have a space-time in gray, and this is electromagnetic field in green. When you go to quantum theory, you discover the photons, the discrete properties of that. In classical generativity, space-time becomes a curved manifold. When you go to the quantum theory, becomes a set of quanta. Okay, these atoms of space describe the mathematics I gave before, but these are not living somewhere in space. This is space itself. So the key idea is that space, if one believes this mathematics, cannot be divided at infinity. The idea, of course, is ancient, right? This is Democritus or maybe Leucippus. What the theory is suggesting is this is not just matter that fails to be continuous and it has a granular structure, cannot be divided infinity, but the space as well. Or if you want the gravitational field as well, that defines something that cannot be broken down at infinity. And since I mentioned infinity, let me just make one side slide. This is more just my own prejudices, but I want to give you them nevertheless, because I think the theory allows this prejudice to be upheld. In quantum gravity, you're allowed to think that there's no infinity in the world at all. And that the mathematics of infinity, the mathematics of continuous that we use is just an approximation for talking about many. The volume of physical space can be finite. Of course, then a lot of modern physics is about impossibilities to go over a certain limit. The maximal velocity of special relativity. Quantum mechanics itself can be viewed as the discovery that phase space, you cannot localize systems in their own phase space more than a Planck cell, right? So there's a minimal size, there's a minimum amount of information you can have about a system. And in quantum gravity, physical space is literally meaningless below a certain scale. And you have a purely combinatorial discrete basis which you can use for doing calculation. So the theory is can be formulated without an infinity. Now let me go to the dynamics, because so far what I've been talking about is results which are several, now maybe 15 years old or more. And again, this is one of Alexander's slides. I found it very nice because it mentioned the two key ideas by Dirac, and that's why I'm saying Alexander very correctly pointed out the split in the directions in which to sort of quantum gravity in these ideas by Dirac, replacing the Schrödinger equation with a direct equation for the transition amplitude, so constructed transition amplitude. The transition amplitude that I gave you in the slide that presented loop quantum gravity are exactly this object here, are amplitudes sort of for going from here to here, where from here to here is another Dirac idea that when you go to four-dimensional field theory, you can use boundary of space-times even in a compact region, compact space-time region, and express the theory as in terms of ability for going from a state here, or at this point the separation of past from the future is not very meaningful. Note that here the state, there's no time, no need to express, to have the amplitude depending explicitly on the time difference between here and here, because the state around it is the state of the gravitational field, and the state of the gravitational field include distances and time separations. So if I'm doing an experiment at CERN, I'm scattering two things, what I need to give the theory to compute the amplitude for something coming out or something else is the incoming particles, the incoming geometry, the outcoming geometry, the side geometry, when the side geometry knows about how much time has gone. So in other words, the state inside knows about everything it has to know in order to do physics. The picture is the following. We can think of a space-time region, a finite space-time region. We have measurement here, and we have just a number which give the amplitude, and loop quantum gravity is a way of defining this number. Now, how to interpret these measurements? Well, with your preferred interpretation of quantum mechanics. If you want to use Copenhagen interpretation, you can think that there's a classical world outside, so there's a CERN machine with people and everything, and there's a small region where you do your quantum gravitation experiment, or there's a black hole, and it's around the classical world, so there's some region inside in which quantum space-time is fuzzy, is ill-defined, whatever you want, but outside you have a classical world, so you make an experiment. Or my own preferred interpretation, which is a relational interpretation, this is a system inside here, outside is another system, so your the amplitude is talking about the information flow between the system, the way one system interact with the other one, which I think is interesting because the picture itself forces us to identify space-time connectivity, being close in space-time with quantum mechanical interaction. I think this is one of the most interesting aspects of that, general, but I don't want to go into that. Now, this transition amplitude, this A, for which are built out of this transition amplitude. Okay, transition amplitude built out of these vertex amplitudes. These vertex amplitudes, there are a number of theorems here. Here names prove the theorems that show that in a certain limit, large J, which means small h bar, go to the Reg Hamilton function. So in an appropriate sense, this amplitude here are a realization of a sum over the sum over geometries. So all this is finite. This is what is interesting about the story. There's no infinite normalization. Why? Because there's a physical scale. This is a scale on which everything is built. The theory can be built without dimensions, right? In units of Planck scale. And I want to mention this. In a sense, it's not a local quantum field theory. It's not a quantum field theory. Right? There's no space-time and local operators. There's never phi of x. So this is definitely outside, in this sense, quantum field theory in the sense of Haag book, for instance, right? Is not a local quantum field theory. Quantum field theory, after Wilson, it's beautifully understood using ideas from condensed matter as a critical phenomenon. So in a sense, you say, well, there's a scale down there. I can send the scale to infinity. What I see is what remains when I send that to infinity. Okay? This is not like that. It's still like condensed matter, but away from critical phenomena, right? If I look at that, there's condensed matter, there's atomic scale here, there's a macroscopic dynamics, this oscillates as waves, but I don't, this is not on a critical point. Air on that is not a critical point. This is not a critical point. There is a finite scale, the atomic scale, and there is a macroscopic limit. There is a finite renormalization group between the two. There is no infinite renormalization group. This is exactly what is happening in quantum gravity. There is a finite scale, the Planck scale. Everything is finite. There's a finite renormalization group. The theory is like condensed matter, but away from critical phenomena. And let me conclude the sort of the presentation of the theory, just going back to the main idea. The states, there are transition amplitudes. In the classical limit, out of the states and transition amplitude, we can reconstruct a space-time. So we can reconstruct this three-dimensional continuum and one-parameter evolution parameterized by clocks and so on and so forth. But time and space are secondary concepts. It does not mean that they don't exist, of course. It's like a chair. Chair is not one of the elementary ingredients of the world. It's made out of something else. So space and time are made up by something else. The primary notion is quantum fields. Quantum fields are many degrees of freedom, the way they interact with one another, and the probability that determines the way that connects, that governs the way, the relation between the way they interact with one another is what the dynamical theory gives up. And I want to stress that because there is a long, I mean, it's not just Kant, but it's all the way to a lot of philosophers that I hear talking today, Tim Modling, I just put one name, who keep insisting that unless there's a primary notion of space and time, we cannot conceptualize the world. I think it's my own view, this is wrong, okay? There is a way of conceptualizing the world which does not require a primary notion of space and time. This is it. I mean, maybe the theory is wrong, but there is a way of thinking, which does not mean that that space is illusory or time is illusory. It only means that it appears at some level of approximation like a table, okay? So it is possible, I believe, to I think that the entire history of science is the same thing. I mean, who started this? You started the talk, I forgot, the day before yesterday, saying, suppose we forget everything and we wake up in this room here, and then we think that all the universe is about a flat ceiling with a little, and then we discover that things are different. So we just update our basic concepts for understanding the world. And we keep doing that, and science is about keep doing that. I think quantum gravity is a step in that, in which we realize that we don't need a continuous space, a continuum time, for giving a fundamental description of the world. These are just things that appear in our own scale, in our own region. How am I doing with time? Can I take a Okay, so can I take a few minutes to talk about physics? This was about the theory in general. So I have a single slide about what you do with the theory, and then I want to tell you about the fast radio burst. So the transition amplitudes are Lorentz invariants, which is not surprising because the Lorentz group is in their very belly. There's a definition. The theory can be coupled to fermions, to Yang-Mills fields. It's not a unification. It's just putting things together, but the things go together well. The Yang-Mills and the fermions is like living on this lattice in some sense, this Planck scale lattice. I've added this because yesterday David Gross said you cannot even derive the Newton force. Yes, it can be derived the Newton force. You can derive the graviton propagator, the general relativity vertices. So the classical dynamics can be extracted by that. There are all sorts of problems, technical problems. There's an issue about how much rigor you demand to the theory. If you demand too much rigor to the theory, you cannot derive anything. But if you're like Kip and me, we're perfectly happy with the derivations. A huge amount of literature is the application to cosmology. This is the modification of the Friedmann equation. There is this extra term here. This extra term gives a bounce in the that replaces the Big Bang. There's a lot of work on black hole thermodynamics. This is an example of a tentative prediction of the way the CMB, the cosmic background radiation power spectrum, is modified at large scales with respect to the standard prediction. As you see, is well inside the statistical errors so far. But I want to zoom. I just want to be fast and zoom to this fast radio burst. And that's a totally different scale than what I said before. What I said before is the work of hundreds of people through decades. This is the work of 4 people in the last year or so. But again, I want to show you what are the kind of efforts to connect this to reality. So here's a story. What happens to matter falling into a black hole? Black holes now are, totally normal objects that astronomers see by the hundreds, thousands in sky. We see matter falling in, star collapse, accretion disk, matter falls in. So matter falls in the black hole. According to the theory, classical theory, there's a singularity, which means the classical theory just doesn't hold there. So something happens there. What does it happen? Well, we need quantum gravity. Where does it happen? Not at the Planck size. Because if I have a star with a certain mass, there is a scale which is its own Schwarzschild radius. So you take the sun is 1,000, it's whatever how big it is, 1,000 times the Earth, and then you squeeze it down to a kilometer and a half. This is a black hole. This is on Schwarzschild radius. So if it collapses, it goes to this size. The Planck length is here, but if the sun collapses, or a star a little bit larger than the sun collapses, it reaches the Planck density when the star is a size much bigger, in fact, more than 10 order of magnitude bigger than the Planck length. This is quantum gravity comes in, not here, here. Right? So quantum gravity comes in at a scale which is a nuclear scale, not at the Planck scale in terms of size of a collapsing star. So this is matter falling in, this is external, this is the Schwarzschild horizon. Much before going really near to the singularity, something must happen. And what happens? Well, if you take quantum gravity and its application, loop quantum cosmology seriously, then what you expect is that there is some sort of pressure, quantum mechanical pressure, that stops the collapse. That's what happened to the universe when it collapses down and then it bounces back when the density gets a Planck density. There is a maximum density in the theory. So what the theory predicts, I'm going very fast here, is that there is some slowing down, weakening of the gravitational force at short scale, and the possibility of the matter to bounce out. So could the matter bounce out, or is this prevented by what we know about the classical theory? Forget Hawking radiation, and just think about quantum gravitational phenomena. Hawking radiation is a dissipative phenomenon, right? It's a heat. If you forget about it, the first hypothesis about a bounce is that it is elastic. So this is a singularity in a conformal diagram. Matter falls in, it bounces like that. This is a white hole. So zero-level hypothesis, a black hole can bounce into a white hole. But everybody knows white holes don't exist, right? We have been told that white hole, it's written in books that white holes don't exist. So I think my interest, this is cute for historians. This is about black holes. In 1972, Steven Weinberg writes in this beautiful book that I use for teaching general relativity that white holes don't exist, most likely don't exist, right? The Schwarzschild singularity does not seem to have much relevance for the world. Was completely wrong, of course, right? We see evidence for the Schwarzschild singularity very strong all over the universe. A little bit later, Bob Wald one of the greatest living relativists, writes exactly the same thing about white holes. The white hole does not seem to play any role in the universe. And one is strongly tempted to say, are you sure, Bob? In a black hole, what is the singularity of the black hole? The singularity of the black hole is a region where the classical theory stops to hold. So where you enter in a quantum gravitational region. What is a white hole? It's a space-time that in the past has a region where classical generativity stops to hold. So that's where you can emerge from a quantum gravity region. So could there be a space-time of that sort? You have some infalling shell bouncing and going out, which creates an horizon, let's say a trapped horizon, so not necessarily an event horizon that goes to infinity. So could the physics here be the one of classical generativity, and that's being a black hole, and the physics here being a class of that of classical generativity, and that's being a white hole, and could there be a transition from one to the other? At first it seems impossible. In fact, we thought it was impossible, but it's not impossible. And it seems impossible because, of course, you can put a white hole and a black hole in the same space-time. That's the Kruskal solution. But the white hole is before, and the black hole is after, right? Here we want a black hole before and a white hole after. And you can do it. Suffice to do that. That was a huge thing. Kip might like it a lot. This is a standard Kruskal solution. Take this gray region, this dark gray region, okay, and cut it out and rewrite it isometrically, just in a different conformal realization here. And this light gray region, and write it this way, and between the two, insert a quantum region. So a region which you expect the Einstein equation are not satisfied. So in other words, open it up and put something in between. That's what you can do in generativity, right? That's all curved space are all about. This is a mathematics. I'm not going through that. I'm just telling you that this metric exists. And what you discover something extremely beautiful. So this is Schwarzschild. This is Schwarzschild. This is the black hole is here. The white hole is here. This is the interior of a collapsing shell, so you can take it to be Minkowski. And now let's compute the time from here to here. So I sit in the star, the collapsing star. The star collapses, bounces back. The time from here to here is proportional to the mass in Planck unit. So for a stellar mass, say, is a millisecond. The time from here to here, so I look at the same phenomenon from outside, at a fixed distance for the star, times m squared, which in user unit is billion years. So what's a black hole? A black hole is a star that collapses, goes inside its horizon, bounces out. It takes a millisecond, boom, boom, immediately. But time dilation is so dramatic that if I look at this phenomenon from outside, I see it in slow motion. It takes billions of years. Right? It's a possible picture of black hole if quantum gravity is such to fill up this region in between, giving what classically is a tunneling probability of going from here to here. What is interesting is that the quantum gravitational region does not go far away, so the rest of the universe doesn't need to be affected by that. Now, m squared is a huge time. So a stellar black hole collapsing today is going to bounce if this happens too much in the future. We're never going to see it. But a primordial black hole could bounce out today, right? And since I know the time from primordial black hole from the early universe to today is a Hubble time, by the m squared of the previous transparency, I can get the size that this black hole should have in order to bounce out today. And I get something of order of millimeters. How do I get something of order of millimeter from a Planck scale phenomenon? Because this is huge factor here, Hubble time of the Planck time. So if this scenario is reasonable, then primordial black holes could be exploding today having sizes of millimeters. Now when we did that, we said, okay, come on, we're not seeing anything with the wavelength of something exploding with a size of a millimeter is make a big boom with a wavelength of that order. And then some of us said, wait a minute, whoops. Parkes, Arecibo, other radio telescope are seeing this fast radio burst, which are very strong pulses of the duration of milliseconds, which are the wavelength is of gigahertz, so wavelength of 20 centimeters. It's not too far from what we computed. Now, it's a wild guess, but it's a possibility, and it shows that it's not impossible that there are phenomena of this sort. So the wild guess being these observed phenomena, could they be quantum gravity? Could they be quantum gravity signals? So let me summarize. I've given you in two presentations, a long one and a short one. A long one is about the theory. I think that the short story is that there is a theory of quantum gravity. It has all sort of holes and things which are not clear yet, of course. But it is well defined. It's a basic set of equations. There's no fundamental space. There's no fundamental time. There's no supersymmetry. The theory is Lorentz invariant, which is what nature is telling us. And it is constructed by taking seriously the picture of gravity as a field and treating it a field, but by taking seriously the idea that gravity is a field and there's no other metric around. There's no other space-time. It's not a field on space-time. It's a field from which the space and spatial and temporal aspects of the world emerge. And then I mentioned that unless we find some sort of empirical confirmation, this remains an hypothesis, which may be right or wrong, like I think all tentative quantum theory of gravity are today. And so the effort to try to connect with observation is strong. And one idea which is recent, I'm very excited about that, that's why I'm talking about that, is that black holes could actually be disrupted by quantum gravitational phenomenon in a time much smaller than the Hawking time. And we might see them, in fact, we might actually already have seen them in this fast radio burst. Thank you.
Thank you very much. There's time for a few questions. Gordon, microphone.
I'll use this. So could you fill in for us a little bit the gap between the sense of Lorentz invariance that you have and the sense of Lorentz invariance that's being, that there are experimental bounds on?
Sure.
I mean, because I take it like, it looks a little like an internal symmetry or something in your theory.
That's a question.
Yeah.
It's actually a question about classical. You can answer by turning it a question into classical generativity. Classical generativity you can formulate in the tetrad formalism and say there's an internal gauge invariance. You can turn the tetrad around as you want. But this, of course, relates to one of the properties of the theory, which is that if I couple an apparatus to the theory, then I can make a Lorentz transformation on the relative position of the apparatus with respect to the universe, to the field, and there's a symmetry. This is a symmetry of the theory, a local symmetry. Technically, you realize there by choosing a gauge, which you attach your tetrad to the legs of your apparatus, and then you realize that what it looks as an internal symmetry in the pure gravity theory becomes a symmetry between two different situations once you have the apparatus. So there is a relation between the internal symmetry and a property of the field. I have a paper which is why gauges recently, which goes into that a little bit. The short story is that the symmetry I'm talking about is the property of classical generativity that locally you have local Lorentz symmetry. Namely, if I make a measurement here, let's talk about rotation, is easier. If I make a measurement here with a local experiment here and I turn it in some limit, there is invariance. Of course, it's a subtle thing of limits, right? Because there's curvature here, curvature has a preferred direction, like we heard from Kip before. So it's delicate, the sense in which there is local Lorentz invariance in GR, but it's clear on the other hand.
So, I mean, can you sort of glue two semi-classical states together in two different ways that differ by, depending on how you think of it, either an internal transformation or a Lorentz transformation that's changing their relationship?
And build up, yes. Absolutely.
My understanding is that the introduction of Ashtekar variables long ago was in a sense a fulfillment of a dream of Wheeler, in the sense that one had a can you hear me okay? Okay. That one had created a kinematical arena in which one automatically fulfilled the three diffeomorphism constraints. In other words, when one was doing canonical quantization, one created operators which were themselves explicitly invariant under the three diffeomorphism group. So one was dealing then with equivalence classes of three geometries. My question, though, has to do with whether there is at least an emergent theory, one in which time appears, in which one can interpret semi-classical solutions at least as exhibiting the full four-dimensional diffeomorphism invariance? Or is there some sense in which one can claim that the objects that appear in this ultimate theory are in fact invariant under the full four diffeomorphism group? Or is that an expectation, is that an unnecessary expectation? Should one desire that of an eventual quantum theory? That is, should one end up with at least semi-classical solutions which exhibit this full four diffeomorphism covariance? Of course, this has to do with the entire problem of the emergence of time in loop quantum gravity.
Yes. Let me separate the conceptual and the technical part of the answer. The conceptual part is the following. If you work with, let's do three-dimensional first and then go to four. If you work with three-dimensional, with symmetric tensors, GAB, then what the three-dimensional gauge theory tells you is that the physics is given by equivalence classes under diffeomorphism. If you work with three geometries, then you have already solved the problem. You don't see three-dimensional gauge invariance anymore. You're working at the gauge invariant level directly.
But you haven't yet done dynamics.
Sorry?
You haven't yet done dynamics.
Three-dimensional. I said let's go in steps. So in the theory here, these three-dimensional states, the quantum states, are already three-dimensional diffeomorphism invariant state. They're, in fact, one way of constructing them is to go through graphs embedded in space-time divided by the actual diffeomorphism group, so you see explicitly. Now, the four-dimensional analog of that goes exactly in the same manner. So when I say that I have a transition amplitude between a three-dimensional state and a three-dimensional state, I'm giving you a three-dimensional state and another three-dimensional state. I'm giving you a number, okay? This number is fully four-dimensional invariant. Concretely, this number is written in terms of a complicated integral. This complicated integral can be rewritten as something that looks very much like a sum of geometries inside. The sum of geometries is dominated in the classical limit, that's what the theorems say, by a four-dimensional geometry, not by a four-dimensional metric. So I see a class of four-dimensional metrics equivalents under four-dimensional gauge transformation emerging. In other words, the classical limit of that amplitude has the property in the classical limit which correspond to a Lagrangian which is invariant in the four-dimensional differential.
But is there a preferred time that arises, or is one free to make? Is one there isn't? So one is free yet to make choices.
Yeah, you can. It's like classical algebra. You can say, well, then it's particularly convenient to use this proper time in this manner, or you can think I can couple a theory to some matter and I have a clock, and that's my clock time. The spirit is, you know, Wheeler went through this idea of the thin sandwich theorem, and then, yeah, okay, that's the same.
Yeah, thanks, that was... I'll be brief. Okay, I had to ask, of course, the one question about the covariance, since you brought it up in the beginning, about the terminology, because there's, of course, several covariances. There's Lorentz covariance, there's general covariance, and in the initial time I was talking about, in the early times, when people talk about covariant quantization, they mean manifestly Lorentz covariant, and that's the criterion. But there, I was just wanted to ask how, for example, in your use of covariant, these different, I mean, you have general covariance, Lorentz covariance, obviously you also have local Lorentz covariance, how there's different notions of covariance and what exactly you're referring to when. And the second question, just a very brief one, you gave this nice list of things that theory can do and can already do, which basically answered all the possible questions I had, and so wanted to ask, what are the things you can't do yet?
Oh, I think that's the right question. Yeah, covariant means all sorts of things. You're right. In fact, I myself use it repeatedly with different meanings. In the title of the book, Covariant Loop Quantum Gravity, what it refers to, and that the main use, the main use I made of the term in this talk, is that the dynamics is not given by writing a Hamiltonian constraint and then trying to find solution of the Hamiltonian constraint and then trying to extract physics from that, but the dynamics is given by giving transition amplitudes. Okay, so these transition amplitudes are given in terms of a complicated integral. The intuition between that is it's like a concrete realization of sum over paths. So covariant in the sense of sum over paths between initial state and final state. In that sense there. Well, let me not answer. I can give you a specific answer about the covariance and the Lorentz, because it goes technical and go into detail. I should distinguish various cases. But your most important question was the other one, namely what's missing. Okay, so what's missing is, apart from the facts, let's take out some physics from that and compare it to nature. But what's substantially missing is the following. The transition amplitudes are given order by order in some expansion. Okay, more and more fine spin forms. At each level, the theory is finite. At each level, we can show that the classical limit goes to the corresponding Regge discretization. What might bring down the full machine is that the correction, when you go to the next level, the quantum correction don't converge at all. And by converge here, I don't mean in the sense of Chandrasekhar, I mean in the sense of Kip Thorne. So I'm not worrying about mathematically proving, we can't do that in QED, we're not going to be able to. I'm meaning I make a calculation at some level of some approximation, I go to Beckler approximation, I want this to not go everywhere. That's not proven yet, and that's, for me, is the, on the theoretical side, the danger that all this might not work.
Thank you. My question is about the way you think about operators. Let's say I have some system and I postulate that its possible states are arrays in Hilbert space. It seems to me that you can define arbitrarily many Hermitian operators, but only few of them are going to be interesting. Then if the physical states of the system are those states in Hilbert space, where do the operators come from?
Oh, very good. I'm happy you asked this question because it allows me to give an emphatical answer. A quantum theory is not, forget gravity, forget special relativity, just go back to quantum theory. A quantum theory is not a Hilbert space and a Schrödinger equation. No, that's gray, there's no information. Quantum theory is a Hilbert space with a given set of operators and a Schrödinger equation. Okay, so I mean, take a particle in 2 dimensions, take a particle in 3 dimensions, the same Hilbert space, the as Hilbert space are the same. The spectrum of the Hamiltonian is the same, so it's the same Hamiltonian. They're 2 different theories. Why they're 2 different theories? Because they're 2 different set of operators. So to give a theory, you have to give the operators, unless you don't have a theory.
Where does it come from in loop quantum gravity?
Where does the metric come from in general relativity? It's the object that defines the theory. I give you a theory. The theory is that these operators, where they come from concretely is I take the classical gravitational field, I construct a representation of a suitable choice of, I'm saying G mu nu becomes this thing here. So in the classical theory, I give the classical theory by saying G mu nu and Einstein equation. In the quantum theory, I give the theory by saying these L operators and these transition amplitudes. But it's always essential in the definition of the theory to say which are the operators that define the theory. Because all are the quantities that determine what I think is reality. Reality are their eigenstate of this operator, okay, or the eigenvalues of this operator, even more. So they're not read out from the Hilbert space in some, they're part of the definition.
So in this model that you give for fast radio bursts, to what extent is that? To what extent is this model you give for fast radio bursts based on this collapse, a quantum regime, and a white hole explosion? And to what extent is that really tied to loop quantum gravity as opposed to some other hypothetical quantum structure in the interior? Where does the loop quantum gravity enter in?
Weakly so, not strongly so. It enters in two manners. In a weak one, 2 manners. In a weak one, which was the origin of that, somehow we took all the results from cosmology and the bounds, and we not much more than intuitively translated to the bounds side. What we're actually trying to do now is to do the dynamics in this quantum region explicitly with a calculation with these amplitudes here from the initial state to the final state. So in principle, the theory should give us an answer of the amplitude, and therefore the probability, and from that compute the key parameter, which is the relation between the mass and the bouncing time. So get to this t proportional to m squared. If we are able to do so, but we haven't yet been, I mean, that's one of the things I'm trying to do with my collaborators, then it will be a proper loop quantum gravity calculation. Now, I expect that if this holds, it's going to be a result of loop quantum gravity, but also of any other coherent theory of not. I don't see anything specifically loopy in the scenario itself.
The crucial thing phenomenologically is that the external time goes as the mass squared in Planck units.
That's the crucial thing.
And where does that come out of? What does that come out of? Is that something that you can tie directly into the loop quantum gravity, or is this you just pull this out of the air?
No, we didn't pull it out of the air. We are trying to. We have 2 or 3 derivations of that, which means that we have non-convincing. We are trying to do this calculation from loop quantum gravity. That's what we are trying to do. So
my hope is that next time we talk together, I can say, look, this is from the amplitude we give this relation. There are other weaker ways of doing that. As you have seen immediately, why people haven't seen this before, right? Because once you see it, you say, well, I mean, why not? Because you need the classical theory to be violated outside the horizon at some point, of course. Otherwise, nothing comes out ever. So the idea is a tunneling effect. So outside the horizon, let's say just outside the horizon, there's curvature, but there's weak curvature. So the idea is a quantum gravity phenomena might happen at given curvature, provided the time is sufficiently long. So if you take curvature and time, you can ask dimensionally when you get to Planck scale. So if you have curvature to some power, time, if you have curvature to time pi, you can compute a length when is. This gives a time, and this gives the m square.
Even though space and time do not belong to our fundamental ontology,